So good afternoon. So dear friends, welcome back to module 3 of fluid pressure and its measurement. So in module 2 the other day we stated what is Pascal's law and proved it, that the pressure exerted by a fluid at a point in a static mass is same in all directions. That is, we proved that the pressure exerted in x direction is equal to the pressure exerted in y direction or in any inclined direction s. So Px equal to Py equal to Ps by assuming a triangular wedge shaped element taken at random from a fluid mass. Then we derived the relationship between atmospheric pressure, absolute pressure and gauge pressure. The gauge pressure at a point can be positive or negative depending on whether the pressure at the point is above atmospheric or below atmospheric. And then again we can have two datums in reporting the pressure at a point. That is, we can take absolute zero, that is complete vacuum, that is the point where the bare minimum pressure can exist, or atmospheric pressure as the datum. When we take atmospheric pressure as the datum, atmospheric pressure is treated as equal to 0 and we report the pressure as above atmospheric or below atmospheric. So above atmospheric it is positive, below atmospheric it is negative, that is gauge negative, and above atmospheric gauge positive. So the convenient way of expressing the pressure at a point is taking mostly in the majority circumstances we take atmospheric pressure as the datum. And absolute pressure at any point is equal to atmospheric pressure plus or minus the gauge pressure. So use positive sign if the gauge pressure is positive and use negative sign if the gauge pressure is negative. And then we worked out some sample problems, that is expressing the pressure in different systems of units as pressure intensity or as a pressure head, again in different columns of liquids, different liquids of different specific weights, and also expressing converting from one system of units to another system of units, that is kgf per centimeter square Newton per meter square. So we worked out some sample fundamental problems in order to understand the concept of pressure intensity and pressure head. And now in this module we will be discussing on measurement of pressure using manometers. So the classification of devices for measurement of fluid pressure can be categorized as manometers in under one category and mechanical pressure gauges on under other category. So they are based on the principle of balancing the column of liquid whose pressure is to be determined by the same or another column of liquid. Suppose say it involves measurement of fluid pressure and the fluid involved is liquid. So balancing the column of liquid whose pressure is to be determined by the same or another column of liquid. Now let us classify the manometers. The manometers can be broadly classified into two categories as simple manometers and then differential manometers. So simple manometers, they are used to measure simply the pressure at a point in a fluid contained in a pipe or a vessel. Whereas differential manometers, they measure the pressure difference between any 2 points in a fluid contained in a pipe or a vessel. So in a pipe means the fluid is flowing, in a vessel the fluid may be in static condition. So simple manometers, they measure the pressure at a point in a fluid contained in a pipe or a vessel. So the fluid may be flowing or the fluid may be in static condition, that is at rest in a vessel. Whereas differential manometers, they measure the pressure difference between any 2 points in a fluid contained in a pipe or a vessel. So let us first discuss on the simple manometers. So let us talk about the construction of simple manometers in general. It consists of a glass tube. So the glass tube, the diameter of the glass tube must be such that there should not be any effect of capillarity, that is the diameter, it should have some minimum diameter in order to avoid the effect of capillary rise or capillary fall, whatever it is. So it consists of a glass tube, and one of the ends of the glass tube is connected to the gauge point. So gauge point is nothing but the point in the fluid stream or the point in the fluid mass where you want the pressure, what you want to record the fluid pressure, or where you want to measure the fluid pressure, and the other end is kept open to the atmosphere. So it is nothing but, say for example, I have a vessel and I want the pressure at the bottom of the vessel. Say this is the free surface, I want say somewhere here at this point. So maybe you can connect a tube here, a glass tube at this point. So what happens, say it contains a liquid of specific gamma, so here water will rise up to this height, up to the free surface. So here P is equal to gamma H, so P at this point, so I want say at point A, so PA is equal to gamma H. So it is nothing but a simple glass tube. So this is a manometer. So we will see this is the simplest form of manometer called piezometer. So when we classify the simple manometers, we will discuss in detail on piezometers shortly following this. So one end is, it has got two ends. One end of the glass tube, this end is connected to the gauge point where the pressure is to be measured, and the other end is kept open to the atmosphere. This is open to atmosphere, this end. So the common types of simple manometers, piezometer, then U-tube manometer, and then single column manometer. So we will be discussing at length the first two types only. The third one, even though it is listed under common types, the usage of single column manometers is less. So you will be coming across piezometers and U-tube manometers in common. Therefore, we will be discussing on the first two. So piezometer. So what is a piezometer? So let us define its construction, explain its construction, and what is its usage. So this is the simplest device, or it is one of the simplest ways of measuring pressure in a pipeline using a piezometer. How? You can drill a hole to the pipeline and connect a tube of small diameter to the hole. Say I want the pressure at the point M. This is a pipeline carrying a fluid. Maybe it can be a, say a liquid, for example. It is carrying a liquid under pressure. So I want the pressure at point, the center of the pipeline M. So I can connect the tube by making a hole in these three fashions. I can make the hole at the top and erect a piezometer like this, or I can make an opening in the side of the tube and bend this tube. This is another form in which the tube can be connected to the pipe. This is another form wherein the hole is made at the bottom and then you have two bends. So in all these cases, if you see that the pressure, the liquid is rising to the same level in all the three tubes, irrespective of where the other end is connected, whether the opening is made at the top or bottom or side of the tube pipe. In all these tubes, glass tubes, the liquid rises to the same height above the center of the pipeline M. So this HM is same in all these three tubes. So the diameter of the tube, as I mentioned earlier, must be small to prevent any disturbance to flow in the pipe, and also you have to ensure that the kinetic energy of the flow does not contribute to the level of liquid in the tube. So the diameter of the tube must be small to prevent any disturbance to flow in the pipe. It should not be too small, because if it is too small, then you will have the effect of capillary rise. So we will be misinterpreting the pressure, or the pressure will be highly estimated, right, than it is actually prevalent if you are using a tube of very small diameter, so that the capillary rise effect is there. So it has to be small from this point, but it should not be too small so that the capillary effect will be absent, and also you have to ensure that the kinetic energy of the flow does not contribute to the level of liquid in the tube. So this tube is called the piezometer. It is nothing but a simple glass tube, one end of which is connected to the gauge point where the pressure is required, and the other end is kept open to the atmosphere. So this is the simplest form of simple manometers. So simplest form of simple manometers, or in case simplest form of manometer we can simply call. It can be used for measuring moderate pressures of liquids. So not high pressures. High pressures you cannot use because you require a long length of tube, which is inconvenient for measuring. So for moderate pressures you can go in for erection of piezometers. So it consists of a glass tube, one end of which is inserted in the wall of the pipe or the vessel containing the liquid whose pressure is to be measured. The other end of the tube extends vertically upward to a height such that the liquid can freely rise in it without overflowing. So the height of the piezometer should be designed or kept in such a fashion that the water should freely rise in it so that you can measure the pressure, and also you have to see that it is not overflowing. The pressure at any point in the liquid is indicated by the height of the liquid in the tube above the point. So it is nothing but what is the pressure? You are measuring the pressure in terms of pressure head in equivalent column of the liquid which is flowing in the pipeline. So this is illustrated in this figure which I had already explained. So let us go to the next slide. Now assuming that the pipe is flowing full, so pipe normally it flows full, liquid is under pressure. What will happen? The liquid will be forced up the piezometer tube to some height measured from the center line of the pipe. This height is known as the piezometric height or the piezometric head. Okay. Suppose if you treat this is as a pipeline wherein the fluid is flowing full. Now when you are making an opening and connecting it to a tube, then the liquid will rise because of the pressure. To what height? Till the pressure at the free surface of the liquid inside the tube is atmospheric pressure. So here the pressure is atmospheric pressure. Here everywhere it is atmospheric pressure. And what you are measuring, the pressure head, this HM, is the gauge pressure. Gauge pressure head in fact. It is pressure head in excess of atmospheric pressure. So we call this as piezometric height or piezometric head. So the elevation to which the liquid rises is the piezometric level. So the principle of the piezometer is that the liquid rises the piezometric tube until atmospheric pressure and the weight of column of liquid in the tube generate a pressure that equals the pressure in the pipeline. So what is the principle of the piezometer? The principle of the manometer we discussed, that is balancing the column of liquid, by the same liquid or some other liquid. So here the same liquid, the principle of piezometer is that the liquid rises in the piezometric tube until the atmospheric pressure and the weight of column of liquid in the tube generate a pressure that is equal to the pressure in the pipeline. So the pressure at the point M in the pipe is indicated by the height HM of liquid in the piezometer above the point M. That is PM is equal to gamma HM. So HM is the pressure head at point M, the center of pipeline. Gamma is the specific weight of fluid. PM is the pressure at the point M in excess of atmospheric pressure. So pressure intensity, gamma is specific weight of liquid. So specific weight of liquid has got units of Newton per meter cube. Pressure head has got units of meter. So this will be Newton per meter square. So PM pressure intensity is in Newton per meter square. So HM is the pressure head. So this is the pressure head. Piezometers can measure only gauge pressures as the liquid surface in the piezometer is exposed to atmospheric pressure. Okay, you can say piezometers can measure only gauge pressures because the liquid surface in the piezometer is exposed to atmospheric pressure. Now, so can you use a piezometer to measure negative gauge pressure? Suppose if the pressure in the vessel is below atmospheric. Say I have a vessel, a closed vessel. So I have a liquid, and please note this is not the free surface, this is not free surface. So you have a pressure here at this surface which is less than atmospheric. So here the pressure is less than atmospheric, less than P atmospheric. So how to measure this pressure which is gauge negative, that is less than atmospheric? So if the pressure inside the container is less than atmospheric, liquid cannot rise. So when will liquid rise? Liquid will rise only when the pressure in the vessel or the pipe is greater than atmospheric pressure. So it rises to a height such that it attains a free surface in the tube wherein the pressure is atmospheric. So, but if you have this arrangement, that is, you at the top of the vessel you erect a tube, bend it, and then the other end of the tube, so one end is connected to the gauge point, this end is connected to the gauge point where the pressure is required, and other end, in the previous case it was kept open atmosphere, in this case it is not open atmosphere, it is kept dipped in a vessel containing a liquid, maybe the same liquid or some other liquid suitably. So if the top of the tube is bent downward and its lower end is dipped into a vessel containing water or any other suitable liquid as shown in figure. So what happens? So what is the pressure prevailing here? Say it can be water or any other liquid. So here the pressure is P atmospheric. Here the pressure is less than atmospheric. So what happens? The tendency of any fluid is to flow from liquid is to flow from high pressure to low pressure. So what happens? As this end is kept dipped inside the liquid in this vessel, and here the pressure acting on the free surface is atmospheric, and here it is not free surface but the pressure is below atmospheric. So what happens now? The liquid rises from here, because the tendency of any liquid is to flow from high pressure to low pressure. So P atmospheric is higher than the pressure inside the vessel, which is less than atmospheric. So it rises to a certain height. Till what height? Till So the atmospheric pressure prevailing at the free surface of liquid in the vessel will drive the liquid up in the piezometric tube to a height h. So this height h will directly give you what is the gauge negative pressure head in the vessel. So the rise of liquid in the tube indicates the magnitude of negative pressure head in the container. So neglecting the weight of air caught in the portion of the tube. So neglecting the weight of air in this portion, we will neglect that weight of air. The pressure on the liquid surface in the container is the same as the pressure at the free surface of liquid in the tube. So this is the free surface of liquid in the tube. Okay. Piezometers can also be used to measure pressure heads in pipes where the liquid is in motion. Okay. In such cases, the piezometer tube should enter the pipe in a direction at right angles to the direction of flow. Suppose, say for example, I have a pipeline and this is the axis of the pipe. So fluid is moving, say, in this direction, left to right. So now here you have to in a direction at right angles to the flow. So the piezometer will enter at right angles, and the connecting end should be flush with the inner surface of the pipe. So glass tubes used for piezometers should not have a diameter less than 12 millimeters. So I told it should have a minimum diameter. So the minimum diameter should be such that it should not be less than 12 millimeters. Why? If a glass tube has a diameter less than 12 millimeters, the effect of capillarity will affect the height of column of liquid. So we want to measure the pressure head precisely. So if you have the diameter of the piezometer or glass tube less than 12 millimeters, then you will have the effect of capillarity, capillary rise. So what will happen? You will measure the pressure higher than what actually it is because of the capillary effect. So therefore, in order to avoid the effect of capillarity, you see that the glass tube used for measurement of pressure in piezometer or manometer have a diameter less than 12 millimeters. So in order to prevent the capillary action, The glass tube should have an internal diameter not less than 12 millimeters. For precise work at low heads, the internal diameter of glass tube should be 25 millimeters. Okay, what are the disadvantages? The disadvantages with the piezometer. Piezometer cannot be used to measure large pressures. As I told, we can use piezometers for measuring moderate pressures. Why not high pressures? Because you require longer length of tubes, which is inconvenient to measure. So piezometers cannot be used to measure large pressures of lighter liquids, particularly liquids with lesser specific weight, because this would require very long tubes and they cannot be handled conveniently. Then the second disadvantage is that piezometers cannot be used to measure gas pressure. You can use piezometers only for measuring liquid pressures. You cannot use piezometers for measuring gas pressures because a gas does not form a free surface. Does not form a free surface. Okay. Now let us take an example on this. In pressure measurement using a piezometer. Example 4, in continuation of the previous examples we have discussed in this chapter on fluid pressure and its measurement. A piezometer measures the pressure in a pipeline carrying water. The piezometer reading is 253 millimeters measured from the center line of the pipe. At this point, what are the gauge pressure and the absolute pressure in Newton per meter square? Take atmospheric pressure as equal to 10.3 meters of water absolute. So I have a pipeline. This is the pipeline which is conveying water. It is conveying water. Say it is carrying water in this direction. Now a glass tube, which is nothing but a piezometer, is attached at right angles to the direction of flow in the pipeline. And because of the pressure at point A, wherein the pressure is required, the water rises to a height of 253 millimeters above the center line of the pipe. So you are asked to find out what is the gauge pressure at this point, what is the absolute pressure at this point in Newton per meter square, and you are asked to take the atmospheric pressure as equivalent to 10.3 meters of water absolute. So let the pressure at point A in the center line of the pipeline is represented as PA. So what is atmospheric pressure? Atmospheric pressure P atmospheric is equal to specific weight of water gamma W multiplied by H. So H is the column of water equivalent to atmospheric pressure, that is 10.3 meters of water absolute. So P atmospheric will be 9810 Newton per meter cube into 10.3 meters of water absolute. So this comes to 101043 Newton per meter square. So atmospheric pressure expressed as pressure intensity is 101043 Newton per meter square. In gauge units, let us express the pressure at point A in gauge units. So what is PA is equal to, PA is equal to gamma W HA. So gamma W is specific weight of water, 9810 Newton per meter cube. HA is the rise of water in the piezometer measured from the point A, which is 253 millimeters. This is HA. This is equal to HA, 253 millimeters. Put it in meters, 0.253 meter, because 1000 millimeters make 1 meter. Therefore, 253 millimeters is 0.253 meter. That is 253 millimeters will be into 10 power minus 3. You will get in meters. (253 millimeter) multiplied by 10 power minus 3 meter per millimeter. So you get 0.253 meter. So PA will be 9810 Newton per meter cube multiplied by 0.253 meter. You get 2482 Newton per meter square. It is gauge pressure, gauge positive. In absolute units, what is absolute units? Absolute pressure at any point is atmospheric pressure plus gauge pressure if the gauge pressure is positive, minus gauge pressure if the gauge pressure is negative, that is vacuum pressure or suction pressure. So here it is gauge positive, therefore use positive sign. So 101043 Newton per meter square is the atmospheric pressure. 2482 Newton per meter square is the gauge pressure, so you get this much. We will move to the next problem. So here this is an inclined piezometer. It measures the pressure in a pipeline carrying water. The piezometer is inclined at an angle of 30 degrees to the horizontal, and has an inclined reading of 330 millimeters. So water rises in this inclined piezometer to a height 330 millimeters, that is inclined height. What is the gauge pressure in the pipeline? So let the gauge pressure at point A in the pipeline be PA Newton per meter square. The gauge pressure at A depends upon the vertical height above A of the free surface of water in the inclined piezometer. So this is the free surface. This is the free surface of water in the piezometer. Now corresponding to this free surface, what is the height of this, vertical height of this free surface from the so that will be, say this is 330 millimeters or 0.33 meter. This is 30 degrees. So I want this height, the vertical height. This is 30 degrees. So I want this height. What is this height? This height will be, this is 60 degrees. This is 90 degrees. So this will be, this is 0.33 meter. So this value, this will be 0.33 into sine 30, because sine 30 is opposite by hypotenuse. That is sine 30 from the right angle triangle is opposite by hypotenuse is 0.33 meter. So this value will be 0.33 sine 30. 0.33 sine 30. So this is the vertical height. So gamma W into H. So vertical height. So 9810 into 0.33 sine 30, that comes to 1619 Newton per meter square. The next problem. A vertical tube contains 200 millimeters of water on top of 270 millimeters of mercury of relative density 13.6. So I have two different liquids, one standing over the other. In fact, the lighter liquid standing over the heavier liquid. The lighter liquid is water, which has a specific gravity of 1 and specific weight of 9810 Newton per meter cube. It is standing over mercury, whose specific gravity is 13.6 or specific weight 13.6 times that of water. So it is a vertical tube. Vertical tube contains 200 millimeters of water standing on top of 270 millimeters of mercury. You are asked to find out what is the pressure at the bottom of the tube here. The bottom of the tube is A. Bottom of the tube is marked as A. So I want pressure at the bottom. PA is equal to how much? So let us start from the top. So because the pressure can be expressed easily as a head, that is P is equal to gamma H. So what is PC? PC is equal to 0, because let us express the pressure at all points in gauge units. So PC is equal to 0, because here it is free surface. This is free surface of water. So the pressure here is atmospheric. PC is P atmospheric, that is equal to 0, because when you are expressing in gauge units, that is when you are taking atmospheric pressure as the datum, atmospheric pressure can be taken as equal to 0. So now let us move to B. What is B? B is the interface of water standing on the top of mercury. Interface of overlying water and underlying mercury. So what is pressure at B? Pressure at B is equal to pressure at that is C plus gamma W H Cb. What is pressure at C is atmospheric, that is 0, plus gamma W we know 9810 Newton per meter cube multiplied by HCb. HCb is this much, that is 200 millimeters or 0.2 meter. 0.2 meter. So, point C in the tube denotes the free surface of water standing over the column of mercury. So, pressure at C is atmospheric, that is in gauge units pressure at C is equal to 0. Now, then, so you can draw the pressure distribution diagram. So, here it is 0, at B it is marked by the pressure intensity is marked by this one, that is PB is equal to, the triangle DF represents the pressure distribution diagram for the 200 millimeter column of water standing over the column of mercury in the tube. So, now the rectangle EFGH, what is EFGH? This one. So, here see this pressure intensity at the interface due to the overlying water will be uniformly felt in this column of mercury, and then in addition to this you will have the varying pressure due to the column of mercury. So, the pressure due to the column of water standing over mercury will be felt uniformly in the height 270 millimeters of mercury. In addition to that, you will have the varying pressure distribution due to the varying column of liquid from B to A. Therefore, the rectangle EFGH represents the uniform pressure distribution due to 200 millimeter column of water exerted in the column AB of the tube. The triangle FHI, that is this triangle, this triangle FHI represents the pressure distribution diagram for the 270 millimeter column of mercury. So, pressure intensity at B is this much, 9810 Newton per meter cube into 0.2, 9810 Newton per meter cube into 0.2, okay. So, you get 1962 Newton per meter square. The pressure at the bottom of tube A is equal to uniform pressure intensity due to 200 millimeter column of water, that is 1962 Newton per meter square, that is PA will be equal to uniform pressure intensity due to 200 millimeter column of water, that is pressure at B plus varying pressure in from B to A due to the standing column of mercury, that is gamma M into HBA. HBA is 270 millimeters. So, PB is what? 1962 Newton per meter square plus gamma M. What is gamma M? Gamma M is nothing but specific weight of mercury is specific gravity of mercury into specific weight of standard liquid, that is water. So, 13.6 multiplied by 9810 Newton per meter cube. So, this one into 0.27. So, 270 millimeters expressed in meters, 0.27 meter this is. So, you get this much, 37984 Newton per meter square. Now, let us move into U-tube manometers. The next category of simple manometers is U-tube manometers. So, whatever limitations you had, right, of a piezometer, that is what are the limitations? We had two main disadvantages. So, piezometers cannot be used to measure large pressures of lighter liquids, and piezometers cannot be used to measure gas pressures. So, these two disadvantages, main disadvantages of the piezometer is overcome by U-tube manometers. So, whatever limitations, that is you want to measure large pressures of lighter liquids and you want to measure pressure of a gas flowing in a pipeline. See, all these things can be done by eliminating the piezometer with the help of a U-tube manometer. So, let us now discuss on the construction of a U-tube manometer. Why it is called U-tube? It resembles the alphabet, English alphabet U. So, one end of the U-tube, say this is one end of the U-tube, is connected to the gauge point. So, A is the gauge point here, at which the pressure is required to be measured. The other end, this is the other end, it is kept open to atmosphere, right. The tube contains a liquid of specific gravity greater than that of fluid whose pressure is to be measured. Say the manometer, the U-tube manometer employs a liquid which has a specific gravity greater or higher than that of the fluid, maybe a liquid or a gas, whose pressure is to be measured. Sometimes even in the manometer you will be using more than one liquid, but in the figure shown we are using only one liquid. There is manometric liquid which is given in dark shade, which has got a specific gravity Sm. So, S standing for specific gravity and M denoting manometer. So, what are the liquids frequently used in manometers? So, mercury, oil, salt solution, carbon disulfide, carbon tetrachloride, bromoform, alcohol. These are all the liquids which are commonly used in manometers. Water is also used as a manometric liquid when it is required to measure pressure of gases or certain colored liquids that are immiscible with water. So, when you are measuring pressures of gases or certain colored liquids which are immiscible with water, then you can use water as a manometric liquid. Otherwise, these are the frequently used manometric liquids: mercury, oil, salt solution, carbon disulfide, carbon tetrachloride, bromoform, and alcohol. The liquids used in manometers should be such that they should not mix with the fluids whose pressures are to be determined. Suppose say you have a liquid flowing in a pipeline, you want to measure the pressure at a point in the pipeline. So, when you are using a manometric liquid, the manometric liquid and the liquid that is flowing in the pipeline should not mix with each other. They should not get mixed. They must be immiscible. They are not mixable. The choice of the manometric liquid depends on the range of pressure to be measured. Suppose if the range of pressure to be measured is very high, say you want to measure high pressures, then you have to use mercury as the manometric liquid because it has got the highest, high specific gravity or specific weight. For low pressure range, you have to use liquids of lower specific gravities. For high pressure range, as I told, mercury is used as a manometric liquid. Now, again, this we have already explained. In figure, the left limb of the U-tube manometer. So, this is called the left limb. This is the left limb. This is the right limb. The left limb is connected to the gauge point, that is A is the gauge point, is connected to the gauge point where the pressure is to be measured, and because of the pressure of liquid at A, what happens, the liquid enters the connected limb, that is the left limb of the manometer, it pushes the manometric liquid. So, to start with, initially what happens in the U-tube, you will see that using this air relief valve, the differential pressure, air pressure is released, the air is released, and you will see that you have to keep the level of manometer, that is the manometric liquid, level of manometric liquid in both the limbs at the same horizontal plane. So, initially the level will be somewhere here, the level of manometric liquid will be somewhere here, this line. Now, when the liquid is flowing, that will be transmitted through the left limb. It will exert, because of the pressure, the column of manometric liquid in the left limb will be pushed down, and accordingly, because of the continuity there, the level of manometric liquid in the right limb will go up. Because of the pressure of liquid at A, it enters the connected limb of the manometer, thereby pushing the manometric liquid and making it to rise in the other limb, that is right limb. So, air relief valve I mentioned, it is provided at the top of the connecting tube, it expels the air and is replaced by the fluid at A. The expulsion of air is important from the point of view of accurate pressure measurement. So that you do not have any differential pressure already. So all these differential pressure because of the air entrainment should be removed. So the air must be expelled out. So for accurate measurement of pressure, the expulsion of air in the column of in the manometer limbs should be important. So pressure at point A can be determined by writing a gauge equation, that is what we call a manometric equation. So a manometric equation can be developed in order to determine the pressure at the gauge point. And U-tube manometers can be used to measure pressures of not only liquids but also gases. That is the second disadvantage which we mentioned in using piezometers for measurement of pressures. So piezometers cannot be used for measurement of pressure of gases. So that can be overcome by employing U-tube manometers. Further, they can be used to measure negative pressures of liquids and gases. So we will work out a problem example involving U-tube manometer. Example 7, the lower part of the U-tube manometer shown below contains mercury of specific gravity 13.6. The pipe contains water. So water is flowing in this pipeline. This is the pipeline. This is the U-tube manometer and this is the left limb. And this is the right limb. Determine the gauge pressure P at the center of the pipe if the manometer readings are as shown in figure. So I want the pressure at point A. This is a gauge point. Say the pressure at the gauge point is PA. So these are the levels. So because of the pressure at A, water is transmitted through the left limb. It pushes the mercury column down in the left limb, and correspondingly the mercury level in the right limb rises to what level? To C. Here the pressure is atmospheric, that is free surface. C is free surface of mercury. The pressure is atmospheric. Here the pressure is say above atmospheric. So let the pressure at the center of pipe A, the gauge point, be PA Newton per meter square. So pressure intensity at B. So where is B located? B is the interface of water and mercury in the left limb. So that is located at a vertical depth 0.5 meter below the gauge point. So when you go down, so pressure increases with decrease in elevation, or pressure increases with the depth. So here point B is at a depth of 0.5 meter below A. That means pressure at B will be greater than pressure at A. So PB will be equal to PA, which is what we require, plus gamma W into Z. What is gamma W? Specific weight of water, because here you have only water. This column is only water. So PA, gamma W, Z is 0.5 meter. Then from B, you are moving to B dash. What is B dash? B dash is a point in the right limb such that points B and B dash are in the same horizontal plane. Points B and B dash are in the same horizontal plane. Same horizontal plane. So what we have derived in module 1, we proved that the pressure remains the same in a horizontal plane. It does not vary. It varies only with the elevation. It decreases with increase in elevation, or it increases with decrease in elevation, or increases with depth. So as B and B dash are in the same plane, even though in different limbs, they are in the same plane, and because of the continuum of liquids, pressure at B will be equal to pressure at B dash, or pressure at B dash will be equal to pressure at B. Then we are moving to C. C, we know what is the pressure at. Pressure at C is nothing but atmospheric, because it represents the free surface of mercury in the right limb. So it is atmospheric. So what is pressure intensity? Is PC is equal to atmospheric pressure, or zero gauge pressure, zero. What is PC? PC is equal to PB dash, that is pressure at B dash, which is equal to pressure at B, which we have already expressed as PA plus gamma WZ, minus Now when you are going up to C from B dash to a higher level. So pressure decreases. What minus? What is it you have in the column B dash C? You have mercury, therefore manometric liquid, specific weight of manometric liquid gamma m into what is the height of C from B dash? It is 0.4 meter. So 0.4 meter. So PC is equal to PB prime minus gamma m into 0.4. Okay. So PB we can express as PA plus gamma W into Z, that is 0.5 minus 0.4 into specific weight of manometric liquid or mercury is 13.6 into 9810, that is equal to 0. So from this you can get what is the value of PA. Okay. This is another problem. A U-tube manometer as shown in figure below is used to measure the pressure in a pipe which carries oil of relative density 0.88. The lower manometer liquid is mercury of relative density 13.6. The surface of separation between oil and mercury is 0.93 meter below the center line of the pipe. The surface of separation between oil and mercury. This is oil column. This is mercury. So this one is 0.93 meter. That is Z is 0.93 meter. If the differential head HM, this is the differential head, HM is 0, what is the gauge and absolute pressure at the center line of the pipe? If Z in figure remains at 0.93 meter, but HM is now 0.037 meter of mercury, what is the gauge pressure in the pipe? Take atmospheric pressure as equal to this much, 101,404 Newton per meter square. So let the pressure at the center of the pipe A be PA Newton per meter square. Pressure at B, what is B? B is at a lower level. So PB is equal to PA plus gamma oil into Z. So PA plus what is specific weight of oil? 9810 multiplied by specific gravity of oil. So this is the standard liquid. Specific weight of water is the specific weight of the standard liquid. Multiplied by 0.88 is the specific gravity of oil into 0.93. So pressure intensity at B dash is PA plus, okay, you get. As B dash in the right limb of the manometer makes the free surface of mercury. Now what is given in the first, now it is B dash C, but if the differential head HM is 0, that means this is 0. That means B dash and C coincide with each other. So in fact it is like this. B dash as well as C coincide with B, the same point. That means HM is 0. So in that case B dash becomes the free surface. So B dash in the right limb of the manometer makes the free surface of mercury. Pressure intensity at B is atmospheric. So what happens? So B dash and B. So here it should be atmospheric. So the pressure head at B is 101,404 Newton per meter square because so the mercury level lies here. That means C is dropping down and coincides B. B dash and B lie in the same horizontal plane. So the pressure must be same as per the proof we have discussed previously in module 1. So this is free surface of mercury means here the pressure is atmospheric. Here the pressure is atmospheric. Now B dash and B lie in the same plane. Therefore here also the pressure should be atmospheric. Okay. So PB is equal to 10104 Newton per meter square. Now PB we have got expression PB dash. So go by this and you get the value of PA. So PA is this much. So you get minus 8029 Newton per meter square, that is in gauge units, negative pressure. So the negative sign indicates that the pressure at A is below atmospheric pressure. that is the pressure at A is gauge negative or suction pressure or what we call vacuum pressure. Then the next one, this is simple. So here you have HM equal to 0.037, that is the free surface of mercury is above the point B dash. So B dash is in the same horizontal plane as that of B. B is the interface of oil and mercury in the left limb. So this you can solve in the same lines as in this problem, the previous problem, example 7. So Z is given. So you can proceed in this fashion. So what is pressure intensity at B? PB is equal to PA plus gamma oil into Z. Then pressure at B dash is equal to pressure intensity at B, as B and B dash lie in the same horizontal plane. Then pressure intensity at C, that is PC, is atmospheric pressure 0. So PC is equal to PB dash minus, because C is above B dash, therefore minus specific weight of the manometric liquid, that is mercury, multiplied by HM, which is 0.037 meter given. So put it and equate it to 0 and get the value of PA. So now PA is minus 3092 Newton per meter square. It is gauge negative. This is gauge negative pressure. Okay. Now example 9. So a U tube containing mercury has its right limb open to the atmosphere. This is the right limb open to atmosphere. The left limb is full of water. The left limb is full of water and is connected to a pipe containing water under pressure. The center of which, the center of the pipe is marked as A, is in level with the free surface of mercury. So free surface of mercury is in the right limb. So the free surface of mercury is in the same level as that of the center line of the pipe. That is very important. Okay. Find the pressure of water in the pipe above atmosphere if the difference in level of mercury in the limbs is 5.08 centimeters. So the difference of levels of mercury is 5.08. So this is the figure. Now it represents the schematic representation of the problem statement, this figure. Now what is required is you have to determine the pressure of water in the pipe, which is above atmospheric. So now here we are expressing in equivalent column. So till now we have been expressing the pressure as pressure intensity. Now for a change, let us express in terms of equivalent column of water. So water is flowing through the pipe. So when you are expressing as water, say for example PA is equal to gamma W at H. So you are expressing in terms of the head. So PA by gamma. So let us write the manometric equation in gauge units. Let the pressure intensity in gauge units at point A be PA. The pressure head at point A in equivalent column of water is PA by gamma W. That is this one, where gamma W is the specific weight of water equal to 9810 Newton per meter cube. So pressure head at B will be pressure head at A. Pressure head at B is a point B here. So A and B are in the same plane, so the pressure will be same, the pressure head is same. Okay. Then it should be noted that for points lying in the same horizontal plane, pressures at all points are the same. Then pressure head at C, what is C? C is, here it will be C, this will be D, sorry, this is D and this is E. So there is some displacement of the letters. So this is C, this is D and this is E. So where is C? I have taken a point in the right limb C, which is in the same level as that of D. D is the interface of mercury, overlying mercury and underlying water in the right limb. So C, where is C? C is located at a distance 5.08 centimeters below B. So pressure head at C in meters of water, because this is full of water. PC is full of water, this is only water, it's water. So PC will be higher, pressure head at B in meters of water plus 0.0508 meters of water. Okay. Then pressure at D, where is D? D is in right limb in the same horizontal plane as that of C. C is in the left limb. So pressure at D will be equal to pressure head at C. Okay. Then pressure head at E, where is E? Sorry, where is E? E is the free surface of mercury in the right limb, which is in flush with the center of the pipeline A. So where is E? E is located at a height 5.08 centimeters above D and this is full of mercury. This 5.08 centimeters of column, 5.08 centimeters column DE is only mercury. So pressure head at E will be pressure head at D minus 0.0508 meter of mercury. It has to be expressed in equivalent column of water because we are expressing all pressures in equivalent column of water. So this column of mercury should be converted to equivalent column of mercury using the expression, say SW into HW equal to SM into HM. So this is known, HM. W stands for water, M stands for say mercury or manometric liquid. So HM is known, this is 0.0508 meter. SM is 13.6 specific gravity of mercury. HW, this is what we want, the equivalent pressure head in column of water, and SW is 1. Therefore, what is HW? HW is equal to SM HM divided by SW. So SM is 13.6 multiplied by HM is 0.0508 meter divided by 1. So that's what, 0.0508 meter into SM by SW. So this is how the column of mercury is converted into equivalent column of water, because we are expressing all pressures in terms of pressure head, and that pressure head is expressed in equivalent column of water. So pressure head at E is equal to pressure head at D in equivalent column of water minus column of mercury expressed in equivalent column of water. That is equal to atmospheric pressure, because E is exposed to atmosphere, there is free surface of mercury. So you will get ultimately, you can go through the expansion of this equation, and ultimately we get PA as you will get 0.64008 meter of water, that is PA. PA can be expressed. PA will be equal to 0.64008 meter of water multiplied by the specific weight of water, that is 9810 Newton per meter cube. You get 6279 Newton per meter square. So if you want to express it in kilogram force per centimeter square, you can do that. That is gauge positive. Okay, thank you. With this, we come to the conclusion of module 3, in which we discussed on measurement of pressure using manometers, and we have discussed at length simple manometers, the first one piezometers and then U-tube manometers for measuring pressure of fluid flowing in a pipeline or in a vessel. So thank you, and let us meet in module 4, in which we will be discussing on measurement of pressure using pressure difference using differential manometers. So thank you.